determine the velocity of a general motion of a rigid body. Okay, so what we'll do is we're going to start with our idea of position. We're going to use relative position. So if I have a body, which I can represent as just a line AB, a rigid body, where I'm going to call that the position of B with respect to A. Okay, if I got that body, I can set up my axes in such a way where I've got a fixed reference as well as a translating reference. And I can set up the fact that the position of point B is simply the position of point A plus the position of B with respect to A. Okay, so then from that I can use displacement, which is ultimately, I need that displacement as a function of time to figure out my velocity. So my displacement, if I think about AB starting in one position and moving to a new position, okay, I think about that basically as a translation. That's where this dotted outline is. So that thing's translating as well as rotating. Okay, so I think about that translation as DRA. So I have DRA to go from A to A and then B to B prime. Then I have a change in the relative position, RB with respect to A. Okay, so then adding up those, I just get DRA plus DRB with respect to A, and that equals DRB. Okay, so that'll give me the displacement of B, knowing the displacement of A as well as the change in the relative position of B with respect to A. So, taking a time derivative of that, I'm just left with velocity, and we've done this before. This is for a relative motion. Okay, VB equals VA plus VB with respect to A. Again, it's just taking the time derivative of the position. No big deal there. Okay. However, now we know some definitions of the time derivative of theta. So again, if I think about that velocity of, just looking at the last term here, the velocity of B with respect to A, that is the time derivative of R of B with respect to A. Okay. Now, if I think about that displacement R of B with respect to A, that is just DRB with respect to A. That is just RB with respect to A times d theta, right? That's the arc length that I've got there. So using that d theta times the length RB. So I've got RB with respect to A, d theta dt. Well, d theta dt is simply omega, so I'm left with R omega. Now, in 3 dimensions, I can think of it, we talked about this last time, where omega R in 3 dimension is actually omega cross R. So I can now write the velocity of point B as the velocity of point A plus omega cross RB with respect to A. And what that essentially is my translation. Okay, so going from having that translation as well as a rotation, which is defined as omega cross R. Okay, so again, this is the translation, V sub A, as well as the rotation, okay, of B with respect to A. Adding those two together, I can actually find the velocity of B, knowing the velocity of A as well as the omega of the object. Okay, just one quick thing that I want to point out with regards to this is when you have rolling problems, the velocity of B, if you're rolling on a flat ground, is going to be horizontal, okay? And it's going to be related to related to omega, knowing the fact that at the contact point, the velocity is 0. So I can find the velocity pretty easily using this equation, knowing that VA equals 0. That means VB is just omega cross R, where R is the radius of the wheel, of B with respect to A. Okay, so omega cross R. Anyway, so if you have a rolling problem, just recognize that at the point of contact, there's no velocity.